All
Well,
right.
I want to start off by saying thank you for taking
Sure.
time out of your weekend and coming
Hey,
here
bet.
to
Yeah.
the Zoom meeting. That's really nice of you.
Well, congratulations on your new role. So
hmm
Thank you.
This is
that's
the
great.
inaugural podcast as well. So you are our first guest ever, which is
Wow. All
Yeah.
right. Uh,
no pressure.
Set the bar low, so there's plenty of room for improvement. That's smart. That's
well, we'll see how it goes, but I'm sure we'll have a lot of interesting things to talk about today.
Yeah, let's get it started. All right.
let's.
We're very much interested in what you studied in university, what you studied in college.
Oh, sure. Yeah. Well, I started out a little undecided. I knew I wanted to study science. And as an undergraduate, I thought, let's just study everything. I went with chemistry, math, and physics. And after about a year of chemistry, I thought, this is really cool, but it's not resonating. And I dropped that for just math and physics. And in the end, I think I just stuck with physics. So at that point, I thought, well, gosh, I need to get on with things and focus in one area. So I'm interested in a lot of things, but only have the dedicated time for physics so far. And as an undergraduate, you kind of study everything. But I was also a summer intern at Lawrence Livermore National Laboratory here in California, and that exposed me to a lot of interesting research in the area of lasers and of X-rays and how those could be used to understand the states of matter in extreme conditions. And when I went to graduate school, then I thought I wanted to study plasma physics, but the person that would eventually become my thesis advisor tricked me into going into working in his lab and building lasers and studying the material property of photocathodes. And I ended up doing something a little bit closer to laser physics and accelerator physics. So a little bit more on the machine building side of things and a little less on the what are the fundamental laws of nature that describe the conditions that you can create with them. And so when I finished my PhD, I was actually interested in sticking with lasers and technology, and I found a job at a small laser company in Los Gatos, California. I went to work there building ultra fast lasers that could produce femtosecond laser pulses, and that company got bought by a bigger company called Coherent, and I worked there for a little while. And then this opportunity came up at SLAC to go a little bit back to using the lasers for research, and that's where I've been now for about 15 years, I guess. So.
Once you started kind of getting more into the technology side, what kind of like relationship would you have with the people who are actually conducting experiments? Obviously, you have the LINAC, right? The accelerator, and it can be directed to multiple different experiments going on at the same time. So if you're working on kind of the mechanics behind it, and they're working on the physics behind it, how do you guys collaborate with that?
Yeah, that's a good question. Right. So maybe I can give you just a quick rundown. You're right. We do have the linear accelerator, or LINAC, as you said. That was originally built at SLAC for doing fundamental physics research in what people call high energy physics, for example, or particle physics. And the idea there was to use that to really probe and understand the fundamental constituents of matter. So one of the results of that was the demonstration of deep inelastic scattering of electrons off of subnuclear particles, which gave very strong evidence that the quark theory is correct, and that protons and neutrons are actually made up of quarks. And when back in those days, the laboratory really kind of only had one mission. It was operate the LINAC to do whatever the most exciting particle physics research was at the time. And that's still how some, high energy physics facilities work. They're really going after one big question. Can we find evidence of the Higgs boson? Yes, Nobel Prize, hooray! All right, can we find evidence of now maybe excited states of the Higgs boson or other decay properties or particles that we don't have evidence for yet? And the whole effort is largely driven toward that kind of one physics goal. What we've done at SLAC now is we've reconfigured the LINAC to be the engine for our X-ray free electron laser. And so free electron laser is it's kind of just what it sounds like. You use electrons to create laser light. And it was an idea invented in the 1970s at Stanford University by a guy named John Mady, who also demonstrated the first one. That laser lased in the infrared. And over the years, people made more and more of these linear accelerator-based light sources, these just free electron lasers in the visible, then in the ultraviolet, and so forth. And LCLS was the LINAC coherent light source at SLAC was the first X-ray free electron laser. So it was the first time we had a bright enough electron beam to be able to produce coherent X-rays. And the way that that's done is the electrons are sent through a magnetic structure called an undulator, where they wiggle back and forth and they emit radiation as all charged particles do when they're being accelerated in some reference frame. Those X-rays then actually become coherent through a process of interaction between the photons that are emitted and the electron bunches. And those coherent X-rays are what produces the laser light. That's what we call it, a laser. Again, that was done for the first time at SLAC. And now there are something like 5 or so of these facilities around the world. So they've gotten quite popular. Getting back to your question, how do those of us who are more focused on making the machine work engage with the scientists who come to use the X-ray source for their research? And I mean, the short answer is, it's a collaborative and iterative process. Generally speaking, we at SLAC work to ensure that we can deliver the X-ray beam in a predictable and reliable way with specific properties. Many of those properties are tunable. For example, the X-ray wavelength can be tuned over something like 3 orders of magnitude in the energy per photon or the wavelength of each of the photons that we're delivering there. And that is obviously a big factor in terms of how the researchers want to use the source. And we have dedicated staff whose job is to ensure that the people that come to use the facility are well aware of what it can and can't do and engage with the users over the course of several months leading up to their experiment to make sure that in the very short time frame that they have to use the facility, they can get the most results out of it. So it's we kind of got standard configurations that people know and love, and then the great thing about scientists is they're always coming up with new ideas and trying to figure out new ways of using the machine. And so that we'll occasionally get proposals to use the machine in new and novel ways that we haven't thought of or that stretch our technical abilities. And then we have to work with the users to make sure that we're able to get some good results, even if we're stretching ourselves a little bit in terms of what the machine can do. Those kinds of interests, let's say, in further development of the capabilities of the machine have driven quite a lot of technical advancement and upgrades to the facility. And at some point, we should talk about cunningly named LCLS2, which is our most recent upgrade of LCLS. But I've talked a lot, so maybe I'll let you ask a follow-up question.
You said that you mainly focused on physics, and then in your PhD kind of went on to more of the technology behind it. I know that you're focusing on it now, but Ben actually had quite a few questions, or seemed very, very interested about some of the stuff that you just recently did that had something to do with fusion. All right.
Yeah, I'm interested in some of the research that you've been doing with the LCLS, the original and the new one, and especially because I was reading about the inertial confinement fusion that you've been doing, because I've never heard of it before. I've heard of fusion in terms of like using the Tokamaks reactors, and it just seems like a very interesting and novel way of creating fusion power, and it seems like something that not many people are doing research on. So I've kind of gone down a rabbit hole today, and I'd be very interested to hear what your take on it is. Yeah.
Oh, yeah, you bet. Yeah. So that's right. I mean, the two, I guess, most popular approaches to controlled fusion energy are just like you said, magnetic confinement in structure like a tokamak, for example. Most popular design. There are other designs too. And then inertial confinement fusion. The basic idea there is, so the idea with magnetic confinement is that you create a stable environment for a plasma, and then you heat it up to a high enough stable temperature where you can sustain the fusion process, which then heats the plasma, and it's a self-sustaining cycle. Inertial confinement fusion is a bit more like what happens in maybe the engine of a gasoline or petrol powered automobile, where you have a small explosion in each of the cylinders, which drives a piston to produce energy, and you do that over and over again. And the fundamental physics behind inertial confinement fusion is that you take a pellet of some hydrogen isotopes, typically deuterium and tritium, and put that inside of a shell with a material on the outside that we call an ablator, and we use optical lasers either directly impinging on the ablator or hitting another material to produce X-rays, and those X-rays then interact with the ablator, cause it to ablate, actually, to vaporize, blow out, and then conservation of momentum causes a compressive force. And if you do that symmetrically enough and fast enough, you can produce a high energy density state that's hot enough to actually drive the fusion process. And that's you can actually think of it almost like a little hydrogen bomb, if you will, going off, because it's essentially the same physics that we have. And one of the major centers of research for that is Lawrence Livermore National Laboratory, where they have the National Ignition Facility, which is the world's most powerful laser that's used specifically for driving these conditions. The global mission is not just sustainable clean energy. There's also a stockpile stewardship element of this, which is what we in the U.S. use as a euphemism for making sure that our nuclear weapons all work the way that they're supposed to. So you can learn a lot about the physics of your nuclear stockpile by studying the microphysics that happens in a implosion event with the same kinds of fuels. So a lot of research driven by our stockpile stewardship program is done. But in addition to that, we have this program for fusion, which has, for the first time, gotten to a burning plasma. So conditions where the energy released by the fusion process has driven more fusion, essentially, right? So And again, there are different thresholds, different Q values, which are the ratio of energy in over energy out. But again, you have to define what you mean by energy in. In this case, the Q greater than 1 is for the energy of in the laser pulse itself. So, something like 2 megajoules of energy, of laser energy, producing, something like I think we've gotten up to maybe 8 megajoules of fusion energy coming out, which is the total combined energy in the neutrons and alpha particles that are produced in the deuterium-tritium fusion process. So, this is actually the only controlled fusion experiment set of experiments that have produced Q greater than 1. And I'll get this back to what I do and LCLS in a minute, but there is actually quite a lot of interest in commercializing this process, and there are several companies actually who are pursuing inertial confinement fusion, so inertial confinement fusion is the physics term, if you will, of what's happening. Usually, the companies refer to it as IFE, inertial fusion energy. It's kind of 2 names for the same thing, but specifically being clear that the goal is to produce energy. Folks use IFE. And of course, there are many, many more companies pursuing magnetic confinement fusion as well. And it's an exciting time because there's been very good progress, especially in private industry in terms of technology development for IFE. There's, I would say there's a clear pathway for developing IFE as a viable power source. There's a lot of engineering challenges, but the fundamental physics, we know that works. So that's a good development. So it's an exciting time. If you're interested in fusion, this is a good time to be in the field because there's a lot happening. There's a lot of private investment. There's a lot of interest from different governments, and it does feel like we're chipping away at it. We're making progress. So at LCLS, at the Linux Coherent Light Source, we do not have the lasers to produce fusion. Again, you need something like megajoules, and there's just only 1 or 2 lasers in the world that currently produce that kind of energy. But we can use the lasers we have to produce conditions of very high pressure and temperature in materials that are used in fusion experiments, and then probe those with the exquisite capabilities of LCLS. So that's the tunable, very bright X-rays with very high time resolution, femtosecond time resolution of the processes that are happening in these materials. So a good example would be just studying the ablator material. Remember, that's the shell that goes around the outside of the fuel in an ICF experiment. And that shell has to be perfect. And I'm not, almost nearly flawless in its construction. Right now, the fuel pellets take months actually to produce. And any kind of small imperfections or cracks or voids or anything like that in those materials can lead to instabilities and non-uniformity during the implosion process, which spoils the process and results in you not getting to the conditions of a burning plasma. So what we can do is at LCLS, we can take samples of the material that are used in these ablators. For example, diamond is a very good sample. Take different crystals of diamond and again produce a compressive shock in small pieces of those that would be in similar conditions to what you would find in an actual fusion experiment, and then probe those with the X-rays to actually understand how imperfections, voids, cracks, any of those things in the microphysics of what's happening in the ablator, how those propagate and result in imperfect conditions in the ablator. We can do similar things for the fuel capsules. For example, a exciting area right now for storing fuel is these wetted foams, these kind of microstructured materials that are used to actually store the hydrogen isotopes for to be actually the source of fuel rather than like little snowballs of deuterium and tritium. It's more putting it into one of these kind of matrices. And so we have a program and a number of researchers at SLAC and Livermore who are interested in studying the properties of these foams, again, on the microstructural scale by using the X-ray scattering and X-ray absorption in a time resolved fashion that we have with the LCLS. So that's a very exciting thing for us right now. It is a high priority for one of the sponsors of the research at SLAC, Fusion Energy Science, which is part of the Department of Energy. And we're very excited to be working with our colleagues at other national labs and in industry to help solve some of the fundamental physics challenges that we have in order to make fusion a robust and reliable energy source.
That's very interesting. I guess it's quite a cop-out question. You probably get asked this a lot, but how far away do you think we are from having a reliable source of energy with fusion?
Yeah. Let me take a swig of coffee and think about that for a minute. So there's a very old joke which you can not avoid running across.
Always 30 years away. Yeah.
That it's always 30 years away. I suppose a modified version of that joke would be, we've made some pretty important advances from when that joke was first made, and so maybe it's down to 25. Now, is it always going to be 25? Yeah, maybe. I don't know. That is a tough one. I guess my way of looking at it is humans have solved really hard problems before. And if you ever get a chance to look at the first transistor, for example, it was, you could see it, right? It was a little wire sculpture essentially that you could see and hold in your hand. And now they are produced in their trillions every day on chips that you can't even, an optical microscope that can't even resolve individual transistors now, practically speaking, right? So there is a proof of principle of the scaling of from a physics concept to engineering, and so my feeling is if we keep at it, we'll get there. We will solve it. You asked the when question. That really, really depends on how much energy we put into this. So if there's a sustained commitment from many humans in their forms of government or corporation or anything else that keeps at this, then we'll get it eventually.
Do we have a good understanding of the physics behind it? Is it mainly an engineering problem, or is it still like we need to do more research into the physics behind it? There is still some physics that we just don't have a good handle on. It's very phenomenological, let's say. So one of the very difficult areas of physics is understanding how instabilities form and propagate in plasmas, which you would find, for example, in the fuel, right? And that is it. That is just a very, very hard problem. And typically it's the kind of thing where you're never going to have a closed form solution. You're never going to have a set of equations that say solve these equations and you'll understand how your plasma is going to work. You pretty much have to do this type of research through simulations. And the simulations can take a variety of different conditions and model how things are most likely to react in different situations. And there are very huge complex codes that look at the hydrodynamics, that look at the heat transfer, that look at the particle and cell models of how these things work. And so a lot of the physics research that we do helps provide
the inputs and parameters that go into those simulations, so that you actually have some idea that your simulation, is predicting a reasonable result. So and I would say we're kind of just at the verge now of starting to get more and more useful information to do that. So yeah, I'd say it's not strictly still just an engineering. Now there are huge engineering challenges to tackle. So, but it's not like the physics is all done and we just have to get more clever about how we build things. We have to do both. So yeah.
I guess when you're thinking, because it is down to how each atom interacts and each particle, it's so small scale and there's so many moving parts, and any slight change, like you said, from pellet to pellet or from fuel source to fuel source, will have such a vast effect.
Right. Yeah, that's right. And again, some things will matter more than others. And we've only done this so many times, and so we don't actually know what all the factors are that influence that. So again, there's a lot of physics that goes into that. The fuel pellet's a great example. It's almost a self-evident example of a real engineering challenge for us right now. The fuel pellets that we make are and the little capsules that they sit in, the little X-ray converter things, which are called hole rooms. Those take, again, months to build, and we shoot them with a laser that shoots once a day. We only do experiments every few months, and so we've only produced Q greater than 1 fusion burning plasmas in it's of order 6 to 10 times. I don't know, quite remember the exact number. In order for inertial confinement fusion, IFE, inertial fusion energy to be a viable source of energy, people think that we need to do this at about 10 hertz, so about 10 times a second. So you can do the math in your head. That's millions of targets a day, just about 1 million targets a day, and so we need to be able to produce those. We need the fuel in order to be able to fill the pellets. So we're going to have fuel production plants in close proximity to the reactors. We've got to have lasers that can fire megajoules at 10 hertz. So that's gigawatts of laser energy. Those lasers have to be pretty efficient, because again, Q equals 1, Q greater than 1 so far has only been achieved for the energy of the laser, not the energy that it took to produce the laser in the first place. So, we've got to close the gap there by a couple of orders of magnitude. So there plenty of engineering. And for your listeners, gosh, we need people to do this work too. I mean, right now, if we had the formula, if somebody came up with here it is, here's everything that we need to do, and with current technology, and all we have to do is turn the crank, we don't have enough human beings that know what they're doing to supply themselves to the fusion endeavor to actually produce all the power. So hooray that you're interested, and hopefully more people will become interested in helping solve these problems.
It's definitely a very cutting edge topic in physics, because a lot of people have the idea that physics is kind of like a subject that we know kind of, we're pretty good, and it's more like our engineering is not up to scratch, but there is so much about physics that we just don't understand, and there's so much more research that we can do and so much more data that we can collect. And I think it's very exciting being a physics student now. And I think it's good to talk about these things and get people excited about the subject.
Yeah. And that's a great segue to point back a little bit at LCLS. So LCLS was the first X-ray free electron laser. It was the first, and if you compare the peak brightness of the X-rays coming from the X-ray FEL to the next brightest X-ray source, which would be a synchrotron, a dedicated, circular accelerator machine to produce X-rays. The peak brightness in the units that the synchrotron people made up for themselves, which are photons per second per square centimeter per square steradian in a 0.1% bandwidth, which they call peak brilliance. Mm-hmm. X-ray FELs are 10 orders of magnitude brighter than synchrotrons.
Wow.
And so, to your point, when you have a source like that, when you have a way of looking at the world that's 10 orders of magnitude bigger in some set of relevant dimensions, you can now actually start looking at things that were not conceivable beforehand. And so having that very high spatial resolution, that very high time resolution, that wavelength specificity, because you can tune the X-rays, it really enables you to go and start looking at fundamental problems, not just in physics, but in chemistry and material science and biology, in a way that you just couldn't before. It's kind of a new window on the world.
Yeah.
When I go ahead.
Yeah. Okay. I was just gonna say, I noticed that you started talking about synchrotrons, and we were talking about LINACs, and that we're probably gonna have people from all of the parts of the department watching this, all the way down to founder.
Yeah.
And I was just wondering if you could just briefly describe the difference between the types of particle accelerators that there
are.
So you kind of get an understanding of what we're talking about when we go over the stuff, the stuff that we've already said, and then the stuff that we're about to.
Yeah, sure. Linear accelerators usually come in one of two shapes, usually circular and straight. Linear and circular, more or less. Sometimes people put them together in like a little, racetrack shape too. So you get a linear section and a couple of curved sections at the end there. Fundamentally, the fundamental difference really is in a linear accelerator, you accelerate the particles once, and then you dispose of them. Either you shoot them into your target, or in the case of LCLS, you run them into an undulator to produce X-rays. I think we get about maybe 0.1% of the energy of the electrons that turn into X-rays, and then all the rest of the electrons get sent down into a beam dump. The circular machines are nice because the particles keep rotating. They keep going around. You can keep accelerating them. You don't have to refill. You can get them going in opposite directions with opposite charges, for example. So our synchrotron was originally built as an electron-positron collider with particles going the opposite way. You take something like the Large Hadron Collider at CERN. That's the same idea, much larger scale, and it uses protons and antiprotons again to produce the high-energy collisions for the fundamental particle research that they do. And so those are kind of the two big differences for, as far as X-ray source. There may be, let's say, three common X-ray sources. The most common, the kind that you find at the airport or at your dentist office, for example, they have a simple static electron accelerator, and they basically just smash the electrons into a target. That produces Bremsstrahlung radiation. It also heats the target. So often you'll get a bright line, for example, from whatever your anode is in that case, say copper. You might get the copper K alpha line, which is around, I think, 9 keV, if I remember correctly, photon energy. That's the most conventional kind of, hit it with a hammer way of producing X-rays. Then synchrotrons again use the short bunch lengths that you can get inside the synchrotron. They run them through magnetic structures as well that cause them to wiggle and produce X-rays. Those are not coherent because the X-rays don't wiggle together long enough to get coherent with each other. And then, but But the great thing about it is you can do this all the way around the ring. So if you have a large enough ring at something like the Diamond synchrotron there in the UK, you can have 50 end stations that can all be operating at the same time. With the LINAC X-ray free electron laser, one of the downsides there is it's hard to split the beam into different undulators or to split the X-rays into different end stations. So we can typically only operate one or two experiments at a time per undulator. Now we can add additional undulators and we can send the beam to different undulators at different times and support different experiments. And we've done that. That's one of the changes that we made with LCLS2. We added a separate undulator, and then we increased the repetition rate of the accelerator. Our old accelerator that was built in the 1960s operates at 120 hertz. It's based on a copper accelerator, which is water cooled. Our new accelerator is a superconducting accelerator made out of niobium, cooled down to about 2 degrees Kelvin. And that's designed to operate at up to almost a megahertz. So nearly a factor of 8,300 or something like that increase in the rep rate of the existing accelerator. And so that high rep rate makes it easy for us to send the beam to multiple different beam lines. Once we build them, they're not particularly cheap or small, so it's a major project to expand our capabilities that way. But then the high rep rate also enables us to look at phenomenon that are much harder to get to with a relatively low rep rate of the current machine, and that can be either in the form of integrating over a long period of time if you have a weak signal and you need to get your signal to noise ratio up, or looking at phenomenon that are fleeting or very hard to find, and or actually looking at the dynamics on the time scale of the time betwbetween the pulses. So actually, things that happen in microseconds or milliseconds, but with femtosecond resolution of what's happening on each one of those shots. So a lot of that technology advancement of going to high repetition rate with the X-ray free electron laser also helps us get closer to what can be done in synchrotrons. I should mention also that synchrotrons typically have a very high repetition rate because they can load up the ring with lots and lots of bunches, and you can get bunches going through producing X-rays at hundreds of kilohertz, for example, or megahertz even.
Said that you did, you did an undergrad and then you did your PhD, and obviously you have to have some kind of motivation to go to school for that many years, right? What kind of, do you remember anything specific that kind of motivated you to get through your undergrad or your PhD or?
Oh, gosh, that's a good question.
Just for any groups that.
Yeah. No, it's a good question. And, I run a summer internship program here too. And so I talk to a lot of undergraduates that are somewhere in their journey of their degree. And I'm always amazed at how often and how much and how deeply this generation thinks about what they're doing. I feel like I came from a generation that didn't have as many obvious options of things to do in the world. So for myself personally, it's sort of like once I picked a path, it felt like, well, okay, that's the path I'm on, and that's what I'm going to do. I'm going to keep after it. So aside from a lack of creativity or motivation on my part, I would say the other factors that helped me get through it all were you or Ben said that there's still a lot to discover. There still really is a huge amount of interesting hard problems to solve in the field, and the more you learn, the more you build on that knowledge, the more you get, you become aware of how much more there still is to do. And I think that helps you maybe see your place a little bit.
Mm.
I think that there is we have access to quite a lot of information now through online sources, and AI makes it appear as though very hard problems can be done very simply with modern tools, particularly with AI. And for sure, these are huge force multipliers, I would say, in our ability to solve problems and different kinds of problems. But it's easy to slip into the idea, again, that we know more than we do, and that it's easy, that just because something can be explained in a 10-minute YouTube video or something like that, that the problem is solved. It's far from the truth. The world is a very, very big place at ground level, and everything is a lot more interesting and challenging than it seems when it's summarized for you. So it's a good question, Jack. I'll try to think of a better answer for you as we're.
No, I thought that was a pretty good answer, because I've noticed, especially for undergrad, I feel like it could be hard for some students to stay motivated, because there's not an immediate, most people aren't doing research in their undergrad and stuff like that. So there's no payoff. There's no physical evidence besides a percentage at the end of the year that you get, I did something. I discovered something. I calculated what I mean.
Right. Yeah, sure. Yeah. So I think the, here's a metric that you can try on for size. Think about, I guess, think about it in terms of the diversity of information and experience that you have. I'm a big advocate for especially, people in their late teens and 20s, not being too quick to hyper specialize on what they're doing. That goes back to, there's just a lot to learn in the universe. There's just a lot to know. And, just focusing on one narrow aspect of things pretty early might shut you out from a lot of gratifying experiences. And I actually think that people that have a kind of a broad diversity of experiences actually become better problem solvers, even in their own specialized field, because they can bring in different perspectives that they have from other expertise or other experience. And there's research that's been done on this too, actually, where they, deliberately get a group of, fairly narrowly focused experts to work on a problem, and a group of very diverse people that come and bring a lot of different perspectives. And usually the diverse group solves a problem faster and better than the hyper specialists. You have to hyper specialize on some things at some point in your career, but don't do it too soon.
Sure.
Take a few extra classes, take things that are outside of your field.
Yeah, sure.
Try out chemistry. I did. Mm-hmm. I don't regret it. But you can also get a little bit caught in the idea that, hey, I got to get this done quick so I can get onto the next thing, so I can get onto the next thing, so I can get on the next thing. And, your life is actually happening right now. So now I'm starting to sound like an old person. I'm sorry.
I found myself doing that a lot this year, kind of looking at my course content and then going ahead. I'm like, well, this other thing, next year, that's a lot more interesting. I'm going to look into that instead. Then I walk into the workshop, because we have a workshop every Friday. And I'm like, oh, maybe I should have looked at this a little bit closer. So I know this is a little bit against what you were just saying, but is there anything, are there any big names in just your specific, what you're doing with Fusion? Is there anything that you could give advice for somebody who's wanting to specialize in Fusion in the future, just finds it really interesting, wants to learn more about it, just something to get excited, or just something that you think
sure
could be?
Yeah, for sure. Yeah. Well, again, it's a very good time now to get educated about fusion and to learn more about it. Uh, let's see. I mean, again, I think we're all physicists here, or physicists in training. You tend to kind of go straight for the physics aspect of things. How what are the conditions? What's a triple point that you need to achieve? What are the conditions of in the plasmas? What are the instabilities that you need to worry about? Those kinds of things. If you're laser minded like me, you're thinking, okay, how many megajoules do I need? What wavelengths are going to work best? Where are we going to get optics that can withstand the average power and things like that? So you can definitely come at this from there's a lot of different angles to tackle this, from a physics perspective. Mm-hmm. And there are a lot of good kind of like reference papers that have been written recently. You can go out and find those relatively quickly, where people talk about kind of what those fundamental questions are that we need to answer. But then I would say learn what some of the other problems are that you need to solve. So a colleague of mine, former director of LCLS, Mike Dunn, says, a fusion energy plant is really a chemical engineering plant. It is, how do you convert your fuel into energy, and how do you use the energy to produce more fuel, and how do you separate the waste products from the things that are actually going to go back into your fuel cycle.
Sure.
So there's quite a massive industrial scale chemical engineering problem that needs to be solved. And then another area that I think comes naturally, let's say, to our colleagues in engineering, but we physicists don't think about so much, is all of the interconnectedness of all of the different systems, all of the controls that go into having a sustained, repeatable and reliable fusion generation process, all the diagnostics and detectors that you need to make sure that your lasers are doing what you're supposed to, or if you're in a tokamak, that your plasma is in the condition that you think it is. Mm-hmm. There's a ton of material engineering that goes into this. The easiest fusion process, if you will, is deuterium tritium fusion, which produces I want to say 14 GeV neutrons. 14 GeV neutrons damage just about every material that we know of, and how fast and how what the consequences are of that damage are things that we need to sort out. How we actually absorb the energy of the neutrons into something that we can generate heat and boil water to run our generators. Fundamentally fusion is just like any other form of energy. At some level, we're boiling water or turning a generator, at least at some level. So I guess getting back to your question, I'd say understand the diversity of challenges, and then find out where you can where you want to learn more, and where you want to maybe try to figure out how to contribute. One interesting problem again is that my friends who are more material science minded than I am is the microphysics of cascaded radiation damage from neutron impingement, and so I have colleagues that look. They actually want to see what an individual neutron does in the lattice of a material, and how that actually creates voids and damage sites. And do those propagate? Do they stay? Do they stay stable? At what fluxes and so forth? It's a real physics problem at the atomic level that eventually leads to the large scale structural questions that you need to answer in order to be able to build a structure that can withstand the kind of neutron flux you'd get in a fusion reactor. So
that's pretty interesting, actually.
Yeah, there's all kinds of interesting problems. So yeah.
Ben, do you have any questions about any of that stuff just now?
I mean, I do find it interesting that it's like so like there's so many different fields that are coming together and working on these big problems now. It's not just like, it's no longer where you've just got one guy or like a couple of people working on a problem. It's like,
Right.
it's beyond borders, it's international, and it's so many different fields and different types of people working on these problems. And it's
Yeah.
almost like,
Yes.
it feels like if you're focusing too much on one specific thing, like you said, it's almost a drawback. You've got to be not just interested in physics, you've got to know what's going on in all the different fields, I think, to maybe not have you've got to have a good knowledge in one specific area, but I think it's important to know what's going on in all fields that are
Yeah.
relevant to your career, really. And I do think it's a really exciting time, and there's never been. It's like, I think technology facilitates it. It's like we can sit down and have a conversation. You be in the other side of the Atlantic, and we can still collaborate as we are. And that's something that humanity has never seen before. Apart from
Right.
the last like 15, 20 years, it's been a thing, and it's just like technology, and there's been so many different strides in science as a result of that, and I think it's a really exciting time.
I definitely agree with you, and there are collaborations specifically, for example, between the UK and the US in multiple areas of science and technology for fusion, for example, and we're working to grow those collaborations, you know, with other countries as well. Unfortunately, some of the countries that are doing really great, exciting, and fast moving research in this area are hard to collaborate with at the moment because of geopolitical reasons, and that's unfortunate. Hopefully, hopefully that gets better in the future. Because it will really take a global effort, I think, to
for sure,
to make this all work for us.
I think science is one thing that will bring people together. And hopefully there'll be, like you say, there'll be changes in the geopolitical state of the world, which because it's not ideal at the moment. But if there's one thing that will improve the conditions, I think science has got a chance.
Yes,
definitely. I mean, I guess you could still have science making big strides with opposing companies as we've seen in the past with space races.
Sure.
Having rivalry can be useful as well.
On those terms in the future.
Yeah.
So that's another interesting thing about fusion right now, I would say, and that is that there are a number of companies who are trying to do do fusion, if you will, produce a fusion pilot plant or a concept for a fusion pilot plant. And they are doing it in kind of what I'd call the, fiercely competitive, keep all the information to yourself, kind of way that a lot of industry has moved forward in the past. And I think it's a little naive to think that any one company, even a huge company, like, General Electric or something like that, or can crack all of these problems on its own. And I think what the Department of Energy in the United States is trying to do, and I think this is also true for governments in the UK and Germany, for example, is to identify areas where really it's going to take a huge scale investment to solve problems that you could kind of call pre-competitive, right? No company is saying we're going to produce all of our own tritium, for example. No. So far as I know, there are no companies that are quite that disconnected from reality in terms of what it would actually take to have tritium, seed production. Now, the thing is, once you get fusion up and running, you can actually breed your own tritium, which is great. You can put lithium in there, and you can absorb neutrons and produce tritium as one of the byproducts of that. Again, huge chemical engineering problem to separate that tritium out from from your lithium absorber in that case. But today there's just not that. There are just only a few sources in the world that are controlled by the government for governments for tritium production, and so that is an example where most companies realize, yeah, hey, we're going to work with the government on this to figure these things out, and there may not be a secret sauce to solving that particular problem, but there are still a lot of companies that are holding their secrets close, and again, that's normal. You don't necessarily want to throw your good ideas out to everyone, especially if others are more capable of exploiting those than you are. That's the nature of capitalism, I guess. So, but again, in the science side of things, lots and lots of fundamental problems that need to be sorted out in order to enable anybody to be successful in driving fusion forward as a future power source. So, yeah. room for lots of room for public-private partnership and pre-competitive research to make sure we solve the big problems with the big resources that are available in the public sector.
All right. Well, I didn't realize how much over the time we've gone, but I hope you don't mind that too much.
I didn't realize there was a time limit. So,
I just gave you the 40-minute. I said, about 40 minutes.
Okay. All right. Yeah, sure. No problem, Jack. That's fine.
Too much, but we like to do both Spotify and YouTube. So,
exciting. Okay.
Physics Society YouTube channel, but apparently it's been lost. So I guess I'm gonna have to.
Reproduce that.
That's your side of things. Yeah.
Got it.
All right, Ben, is there any last comments or anything?
I've really enjoyed talking to you. It's been very, very interesting, very eye-opening.
Great. Yeah. Nice talking to you too, Ben. If you're if you guys get a holiday and you follow Jack back to California, be happy to show you around SLAC. So
I'd love to go to California at some point.
Sure.
I've got no solid plans, but if I ever end up there, I'll definitely let you know.
Sure. Yeah, look me up.
Yeah, and thank you so much for your time this morning. I know it's from your weekend and everything, but
yeah, no problem. This is fun. I'm very happy to talk about what we do, and delighted that you guys picked me for your first podcast. That's super cool. Thank you for that.
Yeah. I thought we had a lot of interesting stuff today.
Yeah, cool. All right.
Okay. Well, thank you once again.
You're welcome. Enjoy the rest of your Sunday and
you.
All right. We'll talk to you later.
All right.
Cheers.